So in this video, what we're going to take a look at is the operation and how a DC motor is working. So there are a few key parts in our circuit, so we're going to identify what those are. So we've got our DC power supply, so that's just a battery, and I'm actually going to decrease the EMF down to 3 volts so our current isn't too big. We've got a rheostat or a variable resistor, so we can change the current in our circuit. We've got the actual motor itself, so we've got the magnets and the windings there, and we'll dig into that in a second. We've got our ammeter over here, so we can measure how big the current is. So the main focus of this video is going to be this motor itself. So let's focus in on that, and we're going to take a look at the different parts. Okay, so the first part that we're going to look at is how we actually set this up. So we've got a north pole on this side over here. So these are slab magnets, and there's a south pole over here. So our field is going across from right to left. So if we're using Fleming's left-hand rule, that means our first or our index finger is going to be pointing from right to left on this screen here. Okay, so the next part that we've got are how we actually connect it to the external circuit. So what you can see here on the outside are two brass brushes. So I'm going to point at those here. So these two are both the brass, well, we call these the brushes. So these are directly connected to the DC power supply. So there's one either side, and they're identical in this case. So that's our connection there. So the other part that we have is we have what's called a split ring commutator. So that's this copper part you can see in the middle. And it's almost a complete ring apart from two splits you can see in it, hence its name, the split ring commutator. And this split in it is important in terms of making the current reverse in a circuit. So essentially what's going to be happening is, so let's say we've got the current coming in from this right hand side over here. If we then rotate it, we can see that this brush is now connected to the opposite side of this commutator here. So the current is always going to be coming in from this right hand side because that's the way we've set it up with our DC battery. And this side of the commutator you can see is connected to this part of the wire. This side on the left of the commutator you can see is connected to the other wire. And so as we rotate it, we're changing the direction that current is going around our circuit. So current always comes in on the right, but we change which wire it's connected to. So before it was connected to the one on the left, now it's connected to the one on the right, and the current is now going round the windings in the opposite direction here. Okay, so that's our setup. So what we're going to look at is, okay, so to know which way the current's going, we have to look at the actual power source itself. So you can see the symbol, one of the lines is longer than the other. And the longer line tells us which side conventional current comes out of. So we can see that conventional current is going to the right. So we can see if we trace it, conventional current is coming out of here, and we can follow the wire around. So it's going to come through the rheostat and along this wire here. And we can see I've actually plugged in my motor the wrong way around. So let's swap that around. So now we can see conventional current is coming in this right-hand side and through this right-hand brush. Then it goes through the wire, around the windings a lot of times, then comes out through the left-hand brush, through our ammeter, and back to our power source there. So that's the direction of our conventional current. So if we look at our ammeter, we can see there's actually already a current going round our circuit. So we'd be like, why isn't this circuit working? And the reason is at the moment the current is too small. So there's essentially not a big enough torque to get this motor to rotate. Friction is essentially stopping it being able to rotate currently. So what we can do is we can actually increase the current in our circuit, and that's what this rheostat is for. And what we're going to do in a second. Okay, so first what we're going to do is actually try and make a prediction about which way we think it's going to rotate using Fleming's left-hand rule. So we know the current is coming in through this brush here. So it's going into this wire, and then so it would go up on this side. So that's the direction of conventional current on this right-hand side. So we're going to point our middle finger upwards and our index finger to the left, because remember, index field points from north to south. Middle finger points in the direction of conventional current. So what Fleming's left-hand rule tells us is this right-hand side of the coil, and we are talking about that one only, will experience a force upwards. Okay, so that's what we're going to see on the right hand side. So we're expecting our right hand side to experience the force and so accelerate upwards. On the left hand side, the current will be coming down. So we need to point our middle finger in that direction. So our first finger doesn't change because the field is still the same, but we can see now the current is coming towards us on the left hand side. Our thumb pointed down, so we'd expect that one to accelerate downwards. So essentially, overall, we're expecting this to rotate in an anti-clockwise direction, a little bit like this. Okay, if the right-hand side goes up, left-hand side goes down, we're going to get anti-clockwise rotation. So let's actually try that out. So I'm going to increase the current very slowly so we can actually see it happen. Otherwise, it will end up spinning too fast. So watch very carefully. So what we're looking for is we're going to get a little jump in a second. So we'll adjust the camera so we can see that a little bit better. So we're not going to set it fully rotating, but we're going to make it jump and make it rotate. So let's have a look. There we go. So you can see the right-hand side has come up and the left-hand side has gone down exactly as we expect. Let's give the current a bit more juice. Now we can see we're still getting the same thing. Right-hand side is going upwards, left-hand side is going downwards, exactly like we'd expect. So let's do that all a little bit quicker so we can see that in action. And we can see this is what actually happens. If we jump the current up really big, we can actually get it to spin at a very fast speed. And the bigger we make the current, the faster we can get it to spin. So what we're going to finish off by taking a look at is actually looking at this in terms of moments and torques. Okay, so what we'll look at is, first of all, what happens if we crank the current up really high. And the unexciting result is even when the current's really big, absolutely nothing happens if we try and start our motor in this position here. So you might think that, oh, something's broken in the circuit. Well, actually it's not. And we know that because the current shoots up, right? So we've got a current in our circuit, so nothing is broken there. It's just that we can't start a motor in this position. So the key is moments here. So that's what we're going to look at. So in this position here, the force on the top one is going to be upwards here because it's still perpendicular to the field and to the current. And that direction will be either up or it will be down at this point. So we're going to say the top one experiences a force upwards. It could be down, it doesn't really matter. So if the top one is experiencing a force upwards, that means the bottom one is going to be experiencing a force downwards. And the key to that is both of these forces are acting in the same line as the axle that goes through the middle here, our axis of rotation. So if the force is up on the top one and down on the bottom one, we get a moment of 0. Whereas in this position here, if there's an upward force on this right-hand side, there is now a perpendicular distance to our axis of rotation, and that means the moment is no longer 0. And it's the same thing on the left-hand side. The moment of the force downwards is not 0, and that's why it can rotate. Because if we have a non-zero moment, that's going to cause our object to rotate. That's the key here. And if we put it back in this position here, however big we make the current, and we can see our current is really big here, it's gone off the scale, the moment is always 0, or the torque is always 0, so it never starts to rotate. So remember in your head, rotation and moments go together. So if it is rotating, there's a non-zero moment. If it's not rotating, there is a moment of 0. I just wanted to dig into that final part a little bit because we're not able to, or at least I at this stage can't draw on the videos to show you. So I want to actually show you that moment thing with a diagram. So remembering, so in this position here, I can't even spell rotation. That's a poor thing. So this one you get no rotation. In this one we got anti-clockwise rotation. Okay, so let's remember that a moment is calculated by multiplying a force by the perpendicular distance to the pivot or the axis of rotation. So if we look at this one on the right hand side, remember we had a force upwards here and we have a force downwards here. So we actually form what's called a couple. So two forces that are the same size trying to make it rotate in the same direction. So this is what we call a couple. So in the equation, the distance is this one, because it's the distance that's perpendicular to the force. So this one, again, this distance is perpendicular to the force. So you can see if we multiply the force by the distance, we're going to get a number that isn't zero, and both of these forces are trying to make it rotate. So there is a resultant moment anticlockwise. And that's why it starts to rotate in an anticlockwise direction. That's caused by an anticlockwise moment. Okay. If we do the same thing over here on the right-hand side, the force looks like this here, because essentially what's happened is this right-hand side has rotated up. So now this force is still upwards because the force is always perpendicular to the field and to the current. So the field is going from right to left. The current is going into the page. So upwards gives us that perpendicular distance. Gives us the force direction using Fleming's left-hand rule. So if I just draw a dotted line, you can see this force is now directly in line with the axis of rotation. So this is what we are calling the axis of rotation here. So those forces are directly in line with that. So the moment is equal to 0 Newton meters here, because the distance is 0. So the force isn't 0, but multiplying it by 0 produces a moment of 0. And that means you get no rotation. Okay, so that's kind of explaining what we're seeing in that last video. I would also like to point out that at this point here, the brushes in contact with the gap in commutator. So this is the point where you actually get the switch over of current. So actually, because the moment was going to be 0 anyway, we actually choose this point to disconnect the current and then be connecting it to the other side because we've got a moment of 0 anyway. So actually, the force is also 0 at this point because the brush is in contact with that split in the commutator and it's about to change to being in contact with the other side. So that's where we've designed our motor specially to make that happen.